From the University of Chicago Podcast Network, this is The Day Tomorrow Began, a special Big Brain series that explores the past, present, and future of some groundbreaking and breakthrough discoveries. On this inaugural episode, Black Holes. I'm your host, Paul Rand. Sometimes the biggest moments in scientific history happen in the most unlikely of places. As we'll see throughout this series, world-changing discoveries don't always happen the way you think. There's no better example than the story of the first person to prove that black holes were not only possible, but probable.
His story is somewhat legendary in the community.
That's Daniel Holz, a cosmologist at the University of Chicago, an expert on black holes, and one of our tour guides for our journey back into the history of black holes.
So a black hole is a region of space-time, of space and time, where essentially their gravity is so strong light can't escape.
Which makes proving their existence, difficult.
By definition, this is the one part of the universe we have no hope of ever observing. Nothing comes out, not even information. Nothing comes out of that. We can't figure out what's actually going on.
This means the proof of black holes was only ever going to happen with pen and paper, equations and theory. There's just one problem.
Well, black holes are absolutely, just by their very nature, they're what results from the complete gravitational collapse of a body.
That's Robert Wald, a theoretical physicist from the University of Chicago and one of the world's leading experts on gravity and black holes.
At least according to classical general relativity, a singularity will form when you collapse a body, but the singularity will be surrounded by a black hole, which is a region of no escape around the singularity.
This thing at the center of the black hole, which we call the singularity, where gravity technically becomes infinitely strong and the equations of physics break down. The general issue of what happens at the center of a black hole, the fact that the equations of physics break down, I think that's terrifying to most theoretical physicists.
Black holes really represent the frontier of our understanding of fundamental physics. And I think that's what intrigues so many people about black holes.
And that's Andrea Ghez, professor of physics and astronomy at UCLA, a Nobel Prize-winning scholar of black holes.
They represent the limitations of our understanding of how the physical world works.
So, for a long time, most people believed that black holes were just simply impossible.
Obviously, black holes can't really exist. And lots of people had that intuition. Einstein also thought black holes were absurd. I think black holes are absurd. They shouldn't exist.
And it's so interesting because Einstein, whose ideas sort of seeded the idea, he was one of the biggest trying to prove that this wasn't the case.
That was until a surprising moment all the way back in 1930.
The version I hear, and of course, within the physics circles, kind of stories get embellished. So a historian may disagree.
If I asked you to picture the exact moment that the idea of black holes was first proven, you'd probably see some white-haired professor sitting in a room surrounded by books and papers. But the real story is far more surprising. So let's actually rewind the clock and take us back to that moment that everything changed. Where are we? What do you see? Okay, we're on a boat. A steamship, to be exact, out in the middle of the Atlantic Ocean. And someone on board is scribbling out equations. It's not some white-haired Einstein, but a young kid, just 19 years old, from India, Subrahmanyan Chandrasekhar.
We just call him Chandra.
Chandra was born in India in 1910, during a time when his country was under British rule.
Nowhere else in the world does a military parade have quite the same air of magnificence as in India. If there's a show to swell the heart of empire with pride, it's Calcutta on parade day.
He may have been raised in a country under the grip of colonialism, but Chandra's family hoped that scientific achievement would transcend that. In fact, his uncle was a renowned physicist who would later go on to be the first Indian to ever receive a Nobel Prize, in any field. Here's Chandra from one of his rare interview appearances.
Pretty nearly made up my mind that I wanted to do science.
And Chandra intended to prove himself.
The pursuit of science has often been compared to the scaling of mountains, high and not so high. But who amongst us can hope, even in imagination, to scale the Everest and reach its summit when the sky is blue and the air is still?
While most 19-year-olds are whiling away their last bits of youth, Chandra was already getting to work. He even wrote his first academic papers at 18. Even the British began to notice this quickly rising star, and he was awarded to study with a full scholarship at Cambridge.
Cambridge, famous throughout the world as a seat of learning, with its rich inheritance from the past, the fine college buildings, its churches, and its culture.
Which brings us back to our steamship in the Atlantic Ocean.
The basic version is that, while on the boat to England, he realized that you have to combine quantum mechanics and relativity when you're trying to calculate what happens to a star at the end of its life.
Little did Chandra know that he was making perhaps the biggest discovery of his life, a discovery that would unlock the secrets of black holes for decades to come.
And so it's related to this question of, when a star burns up all its fuel, what happens? So there are these things called white dwarfs.
White dwarfs, which are held up by the electron degeneracy pressures, the idea that electrons don't like each other.
Quantum mechanics says, you can't have electrons in exactly the same place. And so they push back on each other. And so if you have a bunch of electrons in your star, they'll cause the star to stay big.
Was there a limit to that, to the mass that those kinds of objects could sustain?
Chandra computed an upper mass limit of what could be supported in this way.
And at some point, gravity would overcome this exclusion principle at roughly 1.4 times the mass of the sun.
So stars that have mass greater than 1.4 solar masses would have to collapse beyond the white dwarf stage.
And would collapse further down to either what we now recognize as either a neutron star or black holes.
And that's now called the, Chandrasekhar limit.
When Chandra got to Cambridge, he was sure that the proof of his finding would be irrefutable, but it was met with skepticism.
What people immediately realize is if this is true, then there must be black holes in the universe. And we've talked about black holes are these incredibly radical objects. From a physics perspective, they really should not exist.
Although his math was right, he couldn't get his work published in any of the leading academic papers of the time, and he had to settle for the lesser publication, the Astrophysical Journal.
You never want your equations to say, here's this object, but the object causes your physics to break down. Like, here's an object, it's produced by your theory, but at the center, there's a part where your theory breaks down and you can't describe what happens anymore. That's extremely troubling.
But despite the lack of acceptance for his discovery, Chandra stood by the math, even in the face of ridicule. He knew that he was right, and the debate over his work all came to a climactic showdown in 1935. Chandra was invited to present his findings at the Royal Astronomical Society in London. His talk was to be followed by the most famous astrophysicist at the time, Sir Arthur Eddington, who had seemed to take a great interest in Chandra's work with regular visits to his lab at Cambridge.
Eddington and Chandra talked a lot. It was very respectful and positive by all accounts.
But at the presentation,
it's very well known that Eddington ridiculed Chandra's upper limit.
Eddington basically said, I don't believe any of it. There's a mistake. This can't be right.
Just picture it, a young immigrant presenting his field-defining proof in the highest halls of academic power in the very country colonizing his home, only to be denigrated by the leading mind of that country. The tension in the room must have been palatable.
The lack of approval by one's contemporaries can have tragic consequences when they are expressed in the form of sharp and violent criticisms.
To make matters worse, almost everyone agreed with Eddington.
He was, the leading figure. And for him to say, you're wrong, Chandra was in his early 20s at the time, it was, quite devastating.
They weren't ready to accept that this 19-year-old student from India had seen the truth the rest of them couldn't. But even after this intense defeat, Chandra didn't lose his motivation.
Chandra was young. He was, confident. He understood what the theory was telling him. And he was bold enough to just say, look, they must exist. Like, this is what happens. There's no other story. And people would tell him, we just know you're wrong. He was an unusually confident and capable young man. And he knew he had made a mistake. He went back and he checked it, and he just stuck to it.
Suppose Eddington, instead of finding that I was wrong, had instead said, what you have done is very important. Given Eddington's reputation, it would have made me instantly a very well-known person. I don't know whether that sudden prominence would have been helpful to me in the future. Let me put it this way. Suppose you make an important discovery in the sense that it is immediately appreciated and gives you renown and prestige, then it can, in the long run, harm you because you are diverted from doing science to enjoying, quote unquote, your position in science. And you lose your motivation.
Chandra would go on to become a renowned professor here at the University of Chicago.
I arrived at the University of Chicago in 1974 as a postdoc. And of course, Chandra was here. He had been here for quite some time. He would very often come by to possibly to ask some question about something he was doing, but a little, perplexed by, or to tell me about some result that he had just gotten.
So I was a graduate student at the University of Chicago and was very fortunate to overlap with Chandra for a little while. To me, as a grad student, he was old, but he was very sharp. He was, in his own way, very intimidating, but not in a, you don't know anything, let me tell you the way this really works. His presence, was intimidating because you just knew all the things he'd done. And whenever he spoke, it was this extremely precise, clear, correct statement. And his office was actually just 2 floors below mine here in what we now call the Michelson Center for Physics. And he basically was the major figure in the astronomy department. He was a major figure in the U.S., if not the global astronomy community.
Chandra even became editor of the Astrophysical Journal, which had published his paper back when no one else would. In an ironic turn, as editor, he published the now famous discovery of solar wind by UChicago physicist Eugene Parker, when other reviewers had rejected the paper. Chandra said the math was irrefutable.
The way he kind of steered this journal and had impact through the journal on, what people were working on, and he promoted lots of different work, and he would engage with authors to help them improve their papers and point them in more productive directions. And his influence was so broad. He's one of these figures where I really think it's hard to imagine what the field would be like without him.
I find it slightly embarrassing, if I may say so, because the romance, quote unquote, of my controversy with Eddington, of the early work, and the emphasis on it as a part of my life, I'm afraid it distorts my life.
He made incredible contributions, to stellar structure, stellar dynamics, hydrodynamics, plasma physics, and I'm probably leaving out a couple of other major fields.
As the decades went by, the world of science slowly started to catch up with Chandra's initial achievement.
So what happened in the 60s is that we started to see things that were glowing in the sky that were very, very bright and very far away. These are called quasars. And we now know them to be active galaxies, what we call AGN, active galactic nuclei. And you'll have a galaxy where there's, right at the center of the galaxy, there's something that's just extraordinarily bright. And it's a little non-intuitive, but it turns out the only explanation we have for how to make something so bright is a black hole.
As evidence of black holes continued to mount, it became clear that one of the initial proofs of the existence of this intergalactic behemoth was discovered by a brilliant teenager on a steamship all the way back in the 30s. And finally, in 1983, Chandrasekhar was awarded the Nobel Prize in Physics for this discovery.
Professor Chandrasekhar and Professor Fowler, your pioneering work has laid the foundation for important developments in astrophysics. You have both been the source of inspiration for other scientists working in this field. The remarkable achievements of astronomy and space research in recent years have vindicated your ideas and demonstrated their importance. It is my privilege and pleasure to convey to you the warmest congratulations of the Royal Swedish Academy of Sciences. May I now ask you to come forward and receive your prize from the hands of His Majesty the King.
Black hole research has come a long way since Chandra's groundbreaking discovery. The present and future of black hole research after the break. Big Brains is supported by the University of Chicago Graham School. Are you ready to open the door to new learning in your life? Experience inquiry that is steeped in the UChicago tradition of powerful discovery and exploration. Select from courses and programs in the liberal arts, culture, science, society, and more. Customize your lifelong learning journey with UChicago Graham. Online and in-person offerings are available. Learn more at graham.uchicago.edu/bigbrains. Like Chandra, both Holz and Ghez have made field-defining contributions to the history of black hole research. The discoveries they've made will define where this research goes into the future. For Holz, his breakthrough revolved around something called gravitational waves.
Yeah, so a gravitational wave is a ripple in space and time. You know, everything has gravity. I have gravity. As I'm sitting here, I have if you like, a gravitational force, and I'm pulling on everything around me. Everything that has mass has gravity. So what happens is if you move around, your gravity changes. And what you do is you send off little ripples in space and time. That's what kind of informs the rest of the universe that these changes are happening. So the way I like to think about it is, you know, when I move around, I emit these gravitational waves. They go to the entire universe, out to the very edge of the universe, to tell everything in the universe I've moved, and my gravity is a little different now. And I'm pulling on you, but I'm pulling on you from a slightly different direction. So gravity, these gravitational waves are the way gravity keeps track of where everything is in the universe.
In 2015, Holz was part of a team of scientists that turned on a new piece of technology that they hoped would be able to detect these gravitational waves. It was called LIGO.
Yeah, Laser Interferometer Gravitational Wave Observatory.
We'll just keep calling it LIGO.
We turned them on in 2015 and immediately heard ripples
Ladies and gentlemen, we have detected gravitational waves. We did it.
Which we analyzed, and we realized what we'd heard were the gravitational waves from two black holes colliding into each other.
Truly cosmic news, the sound of two black holes colliding more than 1 billion years ago. It was recorded by a team of scientists at the LIGO Observatory. Proof of gravitational waves, or ripples in time and space, first theorized by Albert Einstein.
And that had never been done before. And this is not, we see some stars going around some mystery object. Or, we have this bright thing far away, we don't have any other explanation for it. This is two black holes crashing into each other. Our theory says very precisely, here's what should happen. You generate these waves, they have a very specific pattern. Lo and behold, we see exactly what the theory says we should see. It's truly remarkable. And I think at that point, there's, that kind of seals it. Like, black holes exist. They're described by Einstein's theory. It took us about 100 years to make this measurement, but we've made it. Everything agrees. And that's it. So black holes are real. There's no way around it.
Today, Holz is working on a new project that will use black holes to possibly find answers to some of the biggest questions in physics. The project involves using something called the Spectral Siren method.
The idea here is we want to use black holes to learn about the universe. If you have two black holes and they kind of merge, so they're in orbit around each other, just like the Earth is in orbit around the sun. Eventually they get closer and closer and they merge because they're emitting gravitational waves. And if you study the waves from that, you can measure how far those objects are. It's like a ruler. Being able to measure the distance to objects in the universe is a very powerful and interesting thing, because if you know the distance to something, you know how long it took light to get to us, because light travels at the speed of light. So you therefore know how far back in time you're looking at this object. And gravitational waves are the same. They also travel at the speed of light. So by measuring distance, we actually figure out, how early in the universe this thing happened. And what it does is it's a way to map the evolution of the universe. And by doing that, we can figure out, is there, what's the nature of the dark matter? What's the nature of the dark energy? Is there something weird about gravity in the universe? So these are big mysteries. These are probably the biggest mysteries, certainly in cosmology right now. What is the universe really made out of? What is the precise age of the universe? These are all things we think we'll be able to answer. And so that's something I'm especially excited about, going forward.
In Ghez's case, her research was focused on searching for black holes' bigger, badder brothers, supermassive black holes.
Of course, as the name suggests, that they're really massive. More like, rather than 10 times the mass, on order of 10 times the mass of the sun, to more like 1 million to 1 billion times the mass of the sun. And those were the ones that intrigued me. I was interested in whether or not these things existed.
In 2018, Ghez would prove not only that supermassive black holes exist, but that there is one sitting at the center of our very own galaxy.
The Royal Swedish Academy of Sciences has today decided to award the 2020 Nobel Prize in Physics with one half jointly to Andrea Ghez and Reinhard Genzel for the discovery of a supermassive compact object at the center of our galaxy.
The tool that we were using is that of measuring the orbits of stars. Orbiting stars tell you how much mass is inside each star's orbit. So you're basically measuring mass, and you want to show that there's a lot of mass inside a small volume. That's how you prove that there's a black hole. Then you need to be able to measure them, and you need to be able to measure them over enough of their orbital period that you can infer what the shape of the orbit is. And these orbits have periods of roughly a dozen years, so it takes a while.
Because black holes emit no light, they are unseeable. But what Ghez did was take measurements of the things we can see. the stars nearby in our galaxy, and their orbits showed they had to be moving around something massive. The only answer could be a supermassive black hole.
So in the case of our galaxy, the black hole at the center is 4 million times the mass of the sun. So it's a very massive object, much more massive than the objects that Chandrasekhar was thinking about. Although in the scale or the realm of supermassive black holes, it's on the light end. So these things that we think today exist at the center of galaxies. In other words, each galaxy should have one supermassive black hole. They range from 1 million, kind of where our galaxy is, to 1 billion times the mass of the sun.
Now, the idea of a supermassive black hole at the center of our galaxy may be somewhat terrifying to think about, but Ghez says not to worry.
Black holes have such bad reputations. There's this notion that's absolutely incorrect, that they're the cosmic vacuum cleaners, that they're sort of this destructive force. And it turns out you have to get incredibly close to these black holes in order for them to have such destructive power. I think of them as more constructive. So if we think of these supermassive black holes as possibly seeds or regulators of galaxies, it's almost like they're the heart of the galaxy, which is a much more maybe less threatening concept. You can't live without them, although I'm not sure that's 100% true, but I think their reputation as bad, destructive objects is misplaced.
Like holes, Ghez is also using her future research to try and tackle some of the deepest questions in physics.
One is understanding how gravity works, so sort of the discovery of new physics and looking for dark matter around the black hole. So the idea that these orbits won't come back to where they started, that the influence of gravity, be it from the black hole or whatever else is around the black hole, will make these orbit precise, like I like to say, like a kid's spiral graph toy. So you take the orbit shape is constant, but it reorients over time. And that's been super interesting because that signal's starting to emerge, and it's not emerging in the way we expected it. So that is one key area. Another area is understanding the population of stars around the black hole. So looking at the stellar evolution of this population. And this population of stars looks nothing like what was predicted, and it has all sorts of surprises. So we're deep into understanding, why do stars not look like what you expected? Is it the black hole affecting the evolution of these stars? Is it the interaction, the dynamical interaction of the system?
Just like Holz and Ghez, Robert Wald also believes that black holes may be our best hope of solving one of the biggest questions in physics today.
The major fundamental problem for the 21st century, perhaps might be the way to put it, is to develop a quantum theory of gravity. I mean, we have an absolutely beautiful classical theory of gravity, general relativity, that's incredibly successful. And we have an almost equally beautiful theory of quantum fields. We understand how to apply quantum mechanics to all fields that we observe in nature, except gravity. Given that we don't have good laboratory experiments to help guide us in developing a quantum theory of gravity, because we can't create the conditions in a laboratory where we would expect effects of both gravity and quantum mechanics to be important enough for us to observe, significant enough for us to observe. Black holes have the potential to, I think they're already providing us to some degree with knowledge like what you might get from experiment. I mean, my hope would be that, as we learn and develop more about black holes, that will give us some additional clues to what a quantum theory of gravity would look like.
We often look to the past for lessons that tell us something about the future. And there seems to be two important lessons that we can draw from the story of Chandrasekhar and Eddington. But those lessons are really two sides of a double-edged sword. On the one hand,
one of the wonderful things about how science works is critiques of science. So pushbacks. Actually, this is something I think that is so central to Chandrasekhar's story. So when we first started to publish our results on the velocities or speeds, people said, we don't believe you. And there's alternative ideas other than supermassive black holes. And people started to publish on what those alternatives were. And the reason this is such an important way in which science works is it forces you to think about how you can come up with better evidence. It's part of the dialogue, and it makes for better science when you can refute the criticism.
But the other edge of that sword is being so confident that you're right, like Eddington, that you can't see what's right in front of you, or you don't even bother to ask the questions that could end up showing why you're actually wrong.
Eddington, it's very easy to vilify him, but he made many important discoveries. He really understood things. It made sense for him to be very opposed to this. It's an extraordinary claim that showed good physics judgment, but it turns out that in this particular case, black holes are real. There is a lesson here, because one of the things I'm very convinced of is that general relativity, Einstein's theory of general relativity, is correct. Everything we've seen says it's correct. There's no evidence that there's anything wrong with this theory. When we detect black holes colliding, it all just agrees. Now, a lot of people are trying to break that theory, because if you could break the theory, maybe you can make dark matter or dark energy go away. Maybe you could make black holes go away somehow. It would be great, because there are all these problems, and maybe breaking the theory would help. If someone comes along and tells me, look, the theory's broken, which we've had. People look in the data and say, look, you see this little bump, the theory's broken. My response in general is, okay, I have two possibilities. The theory's broken, or the data is a little off. The instrument didn't work quite right, or, someone dropped a hammer at the LIGO detector, and that would cause a ripple in our data, or all of Einstein's theory is wrong. I'm going to go with the hammer theory, but I don't want to become Eddington, where someone comes and has really good evidence, and I'm like, no, it just can't be right. I'm not even going to look at it. I just know it's wrong. That's the tricky part. And so I want to be open to the next Chandra saying, but look, here's a thing that doesn't fit your preconceptions.